Jerry mentioned, just wanted to give everyone an overview of all the AI chips and sort of go through what many different companies are doing in the space. So, I came across this code recently. Timothy Prickett Morgan, he writes for the Next platform, and his code was the number of AI chip companies is grows, literally, a dozen. So there are a ton of different companies trying to carve out their own little niche in this whole space. Obviously, there's a lot of demand. The overall market keeps growing, so everybody's trying to see how they fit into this space. And the way I think about the whole market is kind of in a few different ways. So one is you can see what type of device, right? Whether it's a data center, server, or something that you might have, a desktop, laptop, or your phone, your personal computing devices. And then there's like embedded and industrial, like stuff that goes into self-driving cars and robots and those type of things. The other way, another different view is what kind of chip is it, right? So on the left, you have CPUs and GPUs. These are traditionally what is used. And then there's a lot of other custom stuff that's coming in terms of TPUs and other accelerators, right, that don't fit the traditional CPU or GPU mold. And these devices, most of them primarily are data center focused, but they are meant primarily for training, but there's also things that are being used for inference. And then there's this class of products called the NPU, which is really a module. There are very few standalone NPUs. NPU stands for neural processing unit, and these are typically some kind of hardware block that are part of various different chips for your laptop, phone, etc. Right. So these are just a module within a larger chip. So that's kind of how I look at it. Oh, by the way, please stop me anytime. I may not see questions in the chat. I'm focused on this screen. But if you have any questions, please feel free to chime in at any time. So this is the way, like I said, this is the way I like to categorize these different products. So we can go through some of this in more detail, but before we get there, just a quick kind of overview of what is a software, like what are we talking about. So obviously you've all heard of all the different AI frameworks, PyTorch, TensorFlow, etc. So all that gets built on top of the underlying vendor libraries, right? So AMD has ROCm, NVIDIA has CUDA, other companies have different sort of those underlying libraries that ultimately talk to the hardware, and all these AI frameworks are abstractions that live on top of that. And specifically when you're talking about deep neural networks, ultimately all of this boils down to large matrix operations when it goes to at the hardware level. So a lot of this hardware that you will see is basically trying to do these large matrix operations in different ways and in the most efficient way possible. So obviously a lot of the application and the software drives what kind of hardware gets built. And so just wanted to give a quick overview of that before we started looking at the hardware itself. So then when you talk about these deep neural nets, the LLMs, obviously there are two major use cases: the training, the creation of the model itself, and then you have the inference, on the user side. So when you talk about training, it is very bound by memory capacity. So you have these really large parameter models, right? Hundreds of billions, trillions of parameters now. And so even if each parameter were a byte or 2 bytes, you can easily see that this is now going into several terabytes worth of memory. And so no single device can fit all that memory, right? We don't have GPUs or any of these hardware, as you'll see, have that kind of memory capacity. So more than for compute reasons, it's for memory reasons that these large models now need to be split across multiple whatever chips, and then goes into servers and then racks full of servers, right, across a data center. So these models effectively need to be split across all of this and do the training and together, primarily on the training side. And then obviously once you have multiple chips, all the connection links between the chips become very important. So how are chips connected to each other within a sort of a blade, then between different blades in a rack, and then across different racks, right? So I joke that till maybe 15 years ago, the only folks that cared about all of this were the different HPC folks, right, building weather forecasting and all the Department of Energy nuclear simulations type of stuff. But now that kind of knowledge and know-how is now required for building all these computers, and it's being used at a scale that humanity has never seen before. So the demand for that kind of compute is huge, and the only way to build it is to build these very large sets of servers in huge data centers, consuming several hundred megawatts of power. So from a training perspective, most of the computations, at least the ones I have seen, are 16 or 32-bit floating point computations. Again, I'm not an expert in any of this application side, so I'm just trying to simplify what I understand. If I'm wrong, please correct me. But yeah, so a lot of the training happens to be using these floats. I think there are other techniques where I'm trying to reduce it even further, but effectively these are all massive floating point matrix operations. But then when you look on the inference side, these models can be quantized down to smaller sizes. We're talking about 8-bit integers, even 4-bit, 6-bit floating point or 8-bit floating point, down to even 4-bit integers, right? So they're trying to significantly reduce the size of the model so that it can be deployed widely, right, and with less computation requirements and memory requirements as on the training side. And if you taking sorry, was there a question?
Yeah, I got a question.
Yes.
There seemed to be an issue with the slides for a couple minutes there. Something's echoing me.
There seems to be an issue with the slides for a couple minutes there. Something's echoing me.
We're having a problem with recording because it wasn't showing you slides. It was showing a whiteboard with everyone's cursors on it. And when I checked the screen that was doing the recording, it was doing the same thing.
When I checked the screen, it was doing the recording. It was doing the same thing. I just.
Sorry, Jabber. Your voice is like very broken. I think you were saying something wrong with the slides. It's not showing up in the recording.
We all got switched over to whiteboard, but if you click on Shopware screen, it'll come back.
If you click on Shopware screen, you'll come back.
Yeah, your speaker is creating an echo for everyone.
Your speaker is creating an echo for everyone.
Is it from me?
Yes.
Yes.
Let me see. Okay, is that better?
Test.
Seems to be a lot better.
Yes.
Okay. All right. I'm not sure what happened, but so could everyone hear me up to this point or no?
We can hear you.
Yeah, you're sounding better now. But we've missed several slides, though, because the issue with recording when it was on the whiteboard instead.
Oh, I see. I can quickly go back. I don't know at what point, Jabber, we lost the slide.
Yeah, I'm not really sure. I think it was maybe one slide at the beginning, and then went to the whiteboard.
Okay. I mean, we'll post the slides so hopefully folks can go back and refer. But yeah, I mean, just to quickly go through, summary was, what I said was I look at these devices in a few different ways, the AI hardware in a few different ways, kind of where it is used, and then what it's comprised of, right? Whether it's CPU, GPU, accelerators, or these neural processing units. And then quickly spoke up about the software, right? Underlying everything is large matrix operations.
Okay, this slide is the first one.
And then when we talk about neural network training, especially these very large LLMs, there are just several terabytes. Sorry, Jabber, I can't hear you.
I said this neural net training slide. That's the first slide that I don't remember seeing. So I think that's when the whiteboard kicked in, right? Before you started that slide.
Okay, I see. Okay. I think I briefly touched upon them, but we'll post a slide so if somebody wants to follow along, they can look at the slide separately. Okay, so I mentioned that because of the models have to be split across a large number of these chips, the networking between the chips becomes very important. So what is within a single blade in a rack versus connection between the different blades within one rack, and then obviously the network across multiple racks in the data center. And all of these are 16 or 32-bit floats, and depending on how the whole application is sharded across all these different things, at all the intersection points, data needs to be exchanged between multiple nodes. Okay, and then on the inference side, the models are quantized down into much smaller sizes. I mentioned you can go down up to a 4-bit integer value, and then FP6 and FP8 are also very common formats. So really small. So the goal is to keep these models on the inference side as small as possible. And then for LLMs, when you have the prompt phase, which is when you type in whatever you are feeding, that's your prompt that you enter into these chatbots. And that phase, when it's processing the question or the request that you put in, that part is very compute bound. So it's very that's when the GPU or the hardware is doing most of its calculation. But then the token generation phase obviously also has a lot of these matrix calculations. But that when the LLM is spitting out its output, that part is very heavily memory bandwidth bound. And so that's why you will see some of these systems have a very large number of memory channels with a large amount of bandwidth. So another short detour. Since we talked about memory and memory bandwidth, one of the things that is being heavily deployed on the data center side is HBM or high bandwidth memory. And this is, from a bandwidth perspective, massive improvement over your standard DDR or even GDDR memory. And the picture you can see here, it's a 3D stacked set of DRAM chips. And so if you think of this purple die on the side here as your main kind of graphics or CPU die, you have the physical layer, and you have a large number of wires connecting from the GPU GPU PHY over to the HBM controller, which is this die at the bottom, the green one. So normally, if you think about like a DDR channel, it has 64-bit interface per channel or 32-bit interface per channel. HBM is very wide, so 512 bits or 1024. So you have very high number of pins connecting these two, or in this case, bumps connecting the memory to the GPU, and all that goes through a silicon interposer, or they can be like a bridge die. A few different ways in which to do this, and then all the individual DRAM chips are 3D stacked, one on top of each other, and there are connections that go between layer to layer, which we call the TSV, or through silicon vias. These are just copper that goes up and down. And so this provides a massive amount of DRAM bandwidth, but the issue is that the capacity is kind of limited by what is put in. So how many stacks of DRAM and how many of such stacks you have is what governs how much memory you have total. And this is all in the package. So you can see all of this is within one package, and this cannot be upgraded later. So you're basically stuck with whatever you have at the beginning. And so because it's done this way, you get very high bandwidth. But the limitation is that you just can't swap one for like a larger capacity. Like your standard DDR DIMMs, you can't take out the 16 gigabyte one and put in a 32 gigabyte one, for instance. So so whatever is put in the package, that's what you have. And then by now everybody must be familiar with all the memory shortages, and sort of this explains why there is that shortage, right? There's a massive demand for this HBM memory, and all the vendors are basically trying to maximize their HBM production, and therefore the supply of all the other types of memory chips is kind of capacity constrained, and that's driving up prices for everyone. I see a question in the chat. Does HBM require more cooling? Yes and no. I mean, all of this produces heat. The challenge here is that the heat produced by these lower level dies need to get spread out to the top, because you have your heatsink or your liquid cooling plate at the top of this die, and not shown here, but basically, there's the obviously the heatsink is a flat plate at the top, and so there has to be some thermal filler material on top of this die over here, so that heat from here can also reach that cold plate. So you have this all this heat from these lower layers that has to get pulled up to the top and then dissipated out the top. I'm not sure what is happening with my audio. Try to see if something is wrong with my setup. Is it any different now? Did I lose everyone?
No, it still sounds kind of high pitched to me.
I'll continue.
Yeah, it sounds a little odd to me as well.
I promise you I'm not trying to use any filter. I don't know. Do I sound like Darth Vader or something? That would be cool, but...
No, it's more like the Munchkins on the Wizard of Oz.
Or the Chipmunks. You sound like the Chipmunks.
Okay, I will continue. The chipmunk.
So as long as you're interrupted, is this XGMI? Did
I
it
have no
the
idea
protocol
why
between the two physical connections? And is AMD going to start using UA link soon to replace XGMI, or is XGMI going to be around for a while?
Sorry, I can't hear anything either. Not sure what's going on with my audio. Did I hear now?
I'm okay with Elvin. You can stay with it if you like, but
Yeah, it's okay if you keep your speaker down, because then we get the feedback that comes back to us. So
I'm okay with Elvin. You can stay with it if you like. Yeah, it's okay if you keep your speaker.
Okay.
There also seems to be a significant delay between when one of us starts speaking and when we hear it echoing on your end.
Let me.
Yeah, maybe leaving and then just coming back in might work for him.
Does everyone else have the cameras off now, or am I just having a problem with my video? Yeah, oh, I see there. Okay, I guess everyone's just camera off.
So while we're all waiting, what's everybody do here? Are you guys all hardware people, software people, mix, Linux?
Pretty much a mix.
Software, Linux, cryptography.
I'm a software engineer, currently teaching at UMass Boston.
Nice. I'm a SharePoint developer, but doing a lot of AI lately, mostly just development side.
So I'm an assistant admin at MIT Libraries. I do AWS infrastructure administration mostly.
I'm retired now, but I used to be a system administrator, and I also did a lot of system programming. I dabbled a little bit in application programming, but never personally.
I'm mostly a hardware evangelist right now, trying to evangelize RISC-V and numerical notations outside of floating point.
So I just saw that one of the members of the UA-Link working group for the representative for Google Cloud also used to be a RISC-V chair on the RISC-V standard.
Yeah, there's been. I looked at the RISC-V board last week, and there's an NVIDIA employee on the board, and a little eye-opening. I think some folks have gone over to NVIDIA that used to be in the C-suite at RISC-V.
So it would be interesting if UA-Link overtakes RISC-V's essentially bandwidth memory channel and D-Link, right? Because it's an open standard. So if you could get RISC-V with UA-Link inside Google Cloud, that would be pretty interesting in terms of their high performance computing offering.
Oh yeah, yeah.
Shankar's back.
Speech.
Hey, Shankar, can you say something so we can hear what your audio sounds like now? Okay, we're not getting any audio from you at all.
Drum roll, please. Is it Elfin or is Shankar back?
Darth Vader, please.
Somebody suggested that maybe you should dial in on the phone and just use the phone for the voice part.
We can't hear you yet, Shankar.
The dial-in
Well,
number is
Linux did recently just switch from also mixer to pipe. Is that it? But they redid the back end audio of everything.
the dial-in number is in the chat window.
Just to keep the entertainment going till Shankar gets going. How does everybody feel about Anthropic and what they've done over the last couple weeks with national defense and ethics? Does anyone have a viewpoint?
Kind of encouraging. A little bit.
Yeah, I do
Good,
too.
they're hiring.
Good for them. Someone needs to put their foot down.
Yeah, I tend to agree. The other three seem to be jumping in to take their place.
Yeah.
Someone's got to pay for the new ballroom.
No doubt. So I missed the earlier section about the frameworks. It sounded interesting what they were talking about, but it sounded like the hardware would hold or have a certain memory region for frameworks. Did I hear that right?
Yeah, I think they're just having trouble securing memory. I have a Frameworks laptop. I like it.
Yeah, I second that. They're great.
Harumph.
Just my chair. Sorry.
What's the processor in that, Jerry?
In the chair.
An AMD.
I got to play with a deep computing RISC-V based laptop that's completely modular in hardware. I read that a couple of weeks ago. That was really interesting. It's slow, but it's booting up Linux, and you can run Fedora on it.
Works well for me.
So last year, Microsoft announced a quantum processor called Majorana. It's supposed to be kind of building up in processing, but I was wondering if it was tied into this architecture in any way, if anyone knew anything about it.
Yes.
Yes, you're perfect.
Yes, very well.
All right. Sometimes old school works best. Okay. Sorry about that. I should have probably done this earlier. Okay. And my screen is still visible?
Yep.
Okay. I don't know at what point you lost me completely, but I was just saying a couple of things about all this hardware, right? One is networking has become very important, and then memory has become very important. And especially on the memory side, this is leading to a lot of the capacity shortages, right? All the major vendors are trying to shift their production capacity to HBM as much as they can, just for this huge demand from all the different data center customers. So that's if you go to Micro Center and try to buy DRAM today, you'll get a sticker shock. Okay. So any questions on this so far? I know you guys had a lot of other side conversations, but
sounds wonderful so far. Keep going, please.
Okay. All right. I will move on. So let's talk about the actual AI hardware, starting with the data center products. And I'll start with my employer, although I'm not speaking for them today, but this is the AMD MI355 GPU architecture. The next generation 400 series will be coming out, I think, later this year. Some of those details have been publicly announced, and I don't know how much of that is public, so I'm just sticking to the previous generation. So you can see this is one of the GPU chips, and it's composed of these two dies, which we call the IODs or IO dies. That's the base die, and then you have all of these XCDs, which are the compute dies that go on top, and each basic block is built of this shader engine, which is each shader engine is really the like a bunch of floating point units within it. And then there is shared L2 cache, and then this is at the bottom and top are the HBM connection PHYs that I talked about, right? So this is where you would connect to another die at the bottom that has the HBM logic, and then you'll be 3D stacking the HBM memory chips on each of these sides. So you can see we have 4 stacks per IOD, so 8 stacks in total, and then based on whatever capacity that we put, so at least in this generation, there's a total of 288 gigabytes of HBM memory, and a total bandwidth of roughly 8 terabytes per second. So, and then in terms of FP8 performance, it's about 5 petaflops. So each one of these chips, along with, this package, right? This package has 2 of these IODs and a bunch of these XCDs, and then all the HBM memory, all of that go together into one package, and then that can get scaled up in a few different ways. And you can see there are some. There's a PCIe link that connects to the host CPU, which is the AMD EPYC, and then you have a bunch of these other what we call infinity fabric links on either side, and then those can be used to connect to other such dies within other such packages within that within a blade. So that's how this is sort of the equivalent of NVIDIA's NVLink, for folks who are familiar with that. So these get connected over to other of these packages. And then, and this is the next generation MI 400 based products, but you can kind of see how that Infinity Link scales. So you have multiple of these, you have 4 of these GPUs in this one blade, and you have the CPU connected to it, and then how these get connected, it differs from vendor to vendor. On the AMD side, we are big proponents of Ultra Ethernet, which is what is connecting each of these blades to the other ones within a rack. And then inside these things, we have that UA link across. Inside, we call this Ultra Accelerator link, and this is for the connections between GPUs on a single blade. And then the Ultra Ethernet goes over from each of these blades to the other blades within a rack system. So this is an example of a rack. You have all the compute blades, and then you have networking and storage and all the other stuff on it. And then you take each of these racks and then scale out as many as you want within a data center. One of the things I wanted to mention about power, each of these chips, both NVIDIA GPUs as well as AMD GPUs, in this next generation, you're talking about each one of these GPU packages consuming, 1.5 kilowatts roughly of power. And so if you just think of one of these blades with all the networking and everything, you're north of 6-7 kilowatts in just one of these blades. And then you can stack up a bunch of these, and you can quickly imagine on a single rack, how many tens of kilowatts of power you're consuming in a standard 42U rack system. So obviously the challenges are not just on the compute, but how you cool all of this, right? So in the next generation, pretty much everybody is going to a pure liquid-cooled only solution. I mean, there are still some air-cooled variants with a gigantic heatsink, but by and large, I think most of the large-scale deployments are all liquid-cooled. As a question on the die size, I don't know. It's multiple chiplets. Each of these, I forget what the size of this chiplet is. I have to go look up. But we have these 2 chiplets, and then you have all these other shader chiplets stacked on top. I don't know the exact count, but if you take all the area of every single die in this package, it's close to like 2,000 square millimeters, I think. I have to look up the exact number, but you have the base die and all these compute dies on top, and then you have all the HBM memory within this package. So all of that together is a lot of silicon.
I guess what was the resolution? The like 7 nanometers or of each?
So so 7 and 5, I think, are previous generation, and then obviously in the future we're going down to smaller nodes. And each of these, I mean, because these are all different chiplets, each chiplet can be optimized for whatever process makes most sense, right? So the I/O dominated ones would be could be in a larger node, and then the compute dominated ones would go into smaller and smaller nodes. I don't remember the exact one. I should know this, but I don't. I don't work on this product, so it's not at the tip of my tongue right now. But yeah, so I think at least from AMD's perspective, the goal is to be use as many open standards as possible, so that for all of these connect, like the switches, right, to connect these GPUs, or the NICs for the Ultra Ethernet, you have a whole ecosystem of vendors providing those things, and they're not all from one company. Okay, so the next one is NVIDIA. So these are all, again, in the GPU class. So NVIDIA announced their Vera Rubin architecture, and you can see a very similar kind of approach, right? The design is different, but all of these are converging to kind of the same type of structure. You can see that 288 gigabytes of HBM that shows up very common, because that's just how the stacks line up. Rubin has HBM4, whereas the MI355 from AMD was HBM3E. So that's why with the same number of stacks, you can see you have a improvement in the memory bandwidth. So it's a massive 22 terabytes per second of bandwidth and 17.5 petaflops of FP8. And NVIDIA calls these a pod, and a pod is basically 72 of these packages together. So you can see the picture here. You have these two dies connected via this interface between these two chiplets, and then you have the HBM stacks on either side. So similar concept, but this is obviously a newer generation, and so they have more compute, more memory bandwidth in this generation. Yes, I think the symmetry is intentional. They're designing it like that. And then here's the NVLink that then they use to connect to a switch, and that switch hooks up each GPU to multiple other GPUs. And then they have a cache coherent interface on the other side that can connect to the Vera CPU. And so this is how they think about their architecture. So they have their Vera CPU, and then they have the Rubin GPUs connected to that. And on top of this, NVIDIA acquired Mellanox a few years ago, and that was directly because they saw it, and everybody saw it coming, that you need networking and a bunch of other things to scale these GPUs to these large clusters for training these type of large LLMs. So what they announced is not just one chip, but a whole bunch of chips, right? Compute chips, CPU, GPU, the NVLink switch. Then they have their own, I forget the name of the chip, but they have like a network chip that's supposed to hook all these different blades together within a rack, and then how you go across the racks. So a lot of it is based on their own internal products. I think they've pledged to be compliant with some of the other industry standards, but I'm not 100% sure of what is the current state in terms of what they have announced. But you can just see the scale, how you go from a few chips within one blade to these massive racks of systems. So that's NVIDIA, and so it's not just AMD and NVIDIA making these data centers. product. All the data center, all these big cloud providers themselves have decided that they want to do things on their own. You might ask, what about Intel? And I'm not trying to be flippant or anything. I just don't know what their plan is. Obviously, their CPU on the Xeon front, that's a very strong offering, but on the AI accelerator side, the GPU side, there are question marks. So they have their own ARC GPUs. They bought a company in Habana Systems, and they have their Gaudi accelerator, which has some deployments, but nowhere at the scale of AMD or NVIDIA. So it's unclear what they're doing. So I know they're trying to partner with NVIDIA as well. I think both from a fab perspective, right, in terms of manufacturing NVIDIA silicon, as well as using their Xeon as sort of their CPU in certain deployments, right? So instead of Vera and Rubin, they can go Xeon and Rubin. But beyond that, their roadmap is unclear, at least to me. So these are all kind of the vendors who will sell to anybody. And then you have all these other data center and large cloud providers that are doing their own silicon. And these, it's not something you and I can buy, but they are being deployed at a massive scale within their own data centers. And they are using it for their own internal applications, and Google definitely is opening it up for other people to develop and run models in the Google Cloud Platform. So Google has their TPU architecture or tensor processing unit, which is I think their Ironwood generation is now like the 6th or 7th generation. So they've been doing this for a while now, and so it's a kind of a similar. At the end of the day, like I said, a lot of it is just a bunch of floating point units and then a bunch of memory controller, and then the kind of the difference is how all of these are mixed and matched. So they have these vector processing units plus vector memory. So these go into their tensor cores. And then they have all of these sparse compute engines. So one of the things with all these kind of workloads, neural net workloads, is they're very large matrices, but they're also very sparse. So there's a bunch of zeros in them. And so when you're doing matrix multiplication or addition, it doesn't make sense to multiply by 0 or add with something that's a 0. So there's lots of clever ways in which the hardware can deal with that sparsity and avoid doing these wasteful computations, right? When one operand is a 0. So they have these specialized units called sparse cores. I mean, both NVIDIA and AMD also have ways of dealing with sparsity, but Google is kind of interesting that they have their own separate block that does it. And then they also have the same HBM stack that connects to the HBM memory. So and then they have the networking to link multiple of these together. So they haven't quite mentioned how many of them they can hook together in one cluster. Here it says 9216, but I think it's larger than that. It's not very clear, right? Because this is all internal deployments. They haven't revealed a whole lot about this. So that's Google. Next is Amazon with they have two sets of chips, one called Inferentia and one called Trainium, and you you can kind of guess what each of them is for. So Inferentia is obviously for inference, and they have these neuron cores, vector engine, scalar engine, and then they have the neuron link, which is their own network to connect multiple of these inferential chips together. So they have each one of them has 32 gigabytes of HBM and 820 gigabytes per second of bandwidth, and then they can cluster 12 of them together, and that's available in one AWS instance. The other side is Trainium, which is what they use to do their training. This is obviously a much larger chip. They have many more of these neuron cores. They have dedicated DMA engines to be able to copy stuff between the cores and memory, and they have more of these neuron links. So each of these chips has 144 gigabytes. So it's half of the stack that you saw on the AMD and NVIDIA chips, and roughly half the bandwidth. A lot of that scales in terms of how many stacks you have. They're claiming basically 2.5 petaflops of FP8 performance, and then they can cluster 144 of these in one of what they call their ultra servers, and then you can do your training on that level. So I mean, a lot of these are sort of vendors. They themselves are supporting PyTorch and TensorFlow and these type of frameworks on top, and they have their own abstraction layer in the middle to allow these frameworks to run efficiently on their hardware. So, but not much is known exactly what is the software component of them, because you don't have to touch them directly. I think some of the details are not very public. So we talked about AWS, we talked about Google. So Microsoft is a third major player in their Azure offerings. Obviously, I mean, I should mention that all these guys also deploy AMD and NVIDIA. Demand is, because they also offer it to their own cloud customers, right? Some of whom demand, that they have NVIDIA or AMD hardware because their software is tuned towards those. But in parallel, they're also developing all of this. So Microsoft, on the Azure side, they have two chips. That's Cobalt and Maya. And Cobalt is their CPU, which is basically a grid of off-the-shelf ARM Neoverse cores. And then they have two of these chiplets that get glued together, right? So it's not shown to scale here, but this one is a mirror image of what you see on the left. And total of 132 of these ARM cores in this CPU, and then there is like a big L3 that's L3 cache that is shared. Oops, missed this one. So Maya, that's their GPU equivalent, and the details are. They have 200 and then they have 300 coming up. Details on the 300 are not very public yet. 200 this is what they have said. It's 216 gigabytes, 7 terabytes of bandwidth, the massive SRAM internally, and about 5 petaflops. And they can cluster 6,144 of these. So that you go from one chip to a blade, which with I think 4 of them, and then you can rack several of those put them in a rack, and then you have a bunch of racks. So they're also essentially doing the same thing, but in terms of what they're using for their networking and things, it's not very clear. Again, this is all internal, so some external customer wouldn't necessarily have to know these details. And there's Meta. They very recently announced a whole range of products. Meta 300, 400, and 500. And I think 400 is what is currently the latest that is available, and 500, I believe, will come out later this year or early next year. So they have I forget what they call this. Like this is one like processing element, I think they call it, and they have RISC-V based core, and then they have a bunch of these other engines on the side. So they have scalar, the vector, and then there's a command processor that takes commands coming from their main controller, and then just divvies it up to all the different engines within here. And then you take this is one PE, and then they have what they call a PE grid. It's kind of hard to see here, but this light blue thing is a massive grid of these PEs. They have some number, in X and some number in the Y dimension. So there's so they have this fabric interface. So that's the one that's linking all of them together. So it's some kind of mesh network that connects all of these, and then they have HBM on the side. And then PCIe to the host interface. So the commands come down, it gets spread to each of these command processors, and then each of these PEs execute their chunk of that. So again, the architecture, like I said, like a lot of them have settled upon this 288 gigabytes of HBM, 6 petaflops, and then they put 72 of these chips in one, what they call scale-up domain, and there is 1.2 terabytes of bandwidth, bisection bandwidth, in that whole network. So the previous versions of these MTIA chips was primarily meant for their own internal like ranking and recommendation style systems. But I think starting with 400 and going up to 500, they're going to use this for more of the generative AI type workloads, not just ranking and recommendation. And then there's Cerebrus. It's actually a very, very, very interesting architecture. Their whole chip is basically what they could cut out of one wafer. So each wafer is a 300 mm diameter disk, and normally, everybody has the chips within them in a grid, and then you cut off each piece and you sell it as a separate chip. Cerebrus decided to do their design such that whole wafer, they don't dice this up, right? So the only parts that's cut out are the square that goes within the largest square you can fit within a circle, right? And each one of these little things are identical. Like I said, in all the other cases, you would chop this up, right? And then each chip would be sold separately. Here they've decided to put all of that and leave it in what they call wafer scale engine, right? So this whole thing is one big wafer, and kind of it's obviously massive, it's the size of a dinner plate, they've designed it such that they have wires going across these chip boundaries, and they have built a resiliency system where normally you would have defects in manufacturing, and so if there's some defects and let's say this particular chip does not work, then you'll cut it up and throw it away, right? You're not going to sell this. But if you're going to sell all of this, the probability of defects is very high, right, across this whole area, especially when you're talking about manufacturing this at 7 nanometers or 5 nanometer resolution. So the probability of defect in this whole thing is very high. And their design kind of embraces that. They know that there's going to be defects, and they have built a system that kind of routes around it. So they can do a test. They know which parts are defective, even within a chip, right? I'm not talking of this whole chip itself, but all the processing elements that are within each of these. They can mark those as defective, and kind of the software routes around it. Their whole idea is that so we talked about how a lot of these applications are massively bound by memory bandwidth. And so what they did is in each of these things, in addition to those floating point units, they have a massive amount of static RAM, SRAM, on this chip itself. So they have 44 gigabytes of SRAM, and because it's SRAM, it's on the die and running basically at similar clock speeds as their floating point unit. They can get a massive amount of bandwidth, right? So that's 21 petabytes per second of bandwidth, net, right, to all the memories across all these different little units in this big wafer scale chip. And so they don't have directly memory connected to this, but they just have a bus that feeds all the model parameters and distributes it to this 44 gigabytes of memory that's on here. So they only need external memory for storage and things like that. All the processing happens over here, so they don't need to go buy HBM or have any large amount of external memory. Everything is within this chip. And as you can imagine, I don't even remember how many tens of kilowatts it is to cool this chip. And they have videos on talking about some of the engineering challenges that they faced here, and it's kind of fascinating because you have such a large chip, and you have there's thermal gradients, right? Depending on how the workload is running, each portion of this die can be at a different temperature, and expansion, contraction of this as the workload changes, and how that sits on whatever is the motherboard and the substrate that's below, and how you make contact with the heatsink or core plate on top. Those are all kind of big engineering challenges from a mechanical and thermal perspective. And so they've engineered a solution for this. And it's a very, very interesting architecture, very different from what everybody else is doing. So they obviously, because of the size, they have a massive amount of bandwidth and compute capability, 125 petaflops in this one super chip. And then they can put a bunch of these in, or basically each blade is just one of these engines. and then they can make multiple blades in a rack, and then they can cluster all of them together. So kind of different approach, but fundamentally the building blocks are the same. Just how it's constructed and how it's put together is different. Obviously, it has its own pros and cons. Okay. Next is TenseTorrent. This is a startup that was actually found by some ex-AMD people that I know, and they're based primarily in Toronto, and they're basically using RISC-V cores as their basis for their engine. And so they have this thing called the 10.6 core, which is this thing at the top, where they have a bunch of matrix compute engines and vector engines. And then they have these network connections to connect these different cores together. And then they can do atomics and other stuff to a shared memory. And then they have a interface for each of these to the larger chip and clusters of these chips. So they call it a wormhole processor, and that one contains 80 of these 10.6 cores, 292 teraflops, and interestingly, they use GDDR6 memory for this, and they have 12 gigabytes of that and 336 gigabytes per second bandwidth. So they could put a large number of these per rack, 192, and then they have Ethernet linking everything together. So combined 9.3 petaflops per rack. I mean, that's just a few, right? I'm mostly talked about the compute engines. There's other companies, many more than I can possibly cover, right? There's Sambanova, which is, and Grok, which recently got acquired by NVIDIA. Those two companies are mostly focused on just inference. And they have some specific things to do natural language processing and things like that for inference. Then, as you can imagine, the networking for all of this is big now, and at some point, you can only do so much with copper cables, and so now everybody is going towards optics. But not just from rack to rack, everybody's looking at how can we co-package the optics within each GPU or within each of these accelerators, so that we have optical cables coming right out of the edge at very, very high bandwidth and much lower power compared to any kind of copper interconnect. So there's a bunch of other companies. There's Light Matter, which is looking at something like this. So there's a lot of focus on optics and how we do very, very efficient optical networking between these different products, between different. How you build a cluster out of an all optical networking system. Okay, so that's kind of the major ones on the data center side. And I have a few more slides to talk about what's going on the PC edge and kind of industrial side of it. The market for this is also expected to grow a lot. More and more compute you want to do locally, just for latency reasons and also for privacy reasons. So for all kinds of reasons, for data that you don't want to be sending to these cloud providers, you want to do as much inference, primarily inference, locally. So almost every laptop and phone chip that's being sold today has some kind of neural processing engine to do some of these inference processing locally. Again, I'll start with AMD. All the latest last few generations of the Ryzen, particularly the laptop products, not the pure desktop ones, but the ones meant for laptops have this Ryzen AI branding, and they have an internal NPU or neural processing engine to do efficient neural network inferencing. So the biggest and baddest of them is what we call the AI Max, and it is also was previously codenamed Strix Halo, and it's a very big chip. It has up to 16 of our Zen 5 CPU cores, a very large GPU engine, up to 40 compute units for the GPU, and 50 TOPS or teraops per second. That's just a term folks use for int8 compute capability, right? So 50 tera operations per second of integer 8 performance. And then most of our desktop and laptop products have 128-bit memory interface. This Max products have twice that, so 256-bit interface, and that's why you see a much higher memory bandwidth. So both for gaming as well as for inference, that's a big advantage, having that really wide memory bus. Apple doing the same thing. They've actually also been doing it for quite a while now. So if you look at the M4 Max and the more recent M5, there's dedicated silicon. I just wanted to highlight, right, of this area, how much of the chip real estate is dedicated to these neural units. So just everybody's betting that a lot of the workloads want to be run locally, and everybody's investing a ton of silicon die for that. So the M5 has 16 of these neural cores. They don't quite mention what TOPS they have, but they also have 10 of these GPU cores, and some of the applications can be run on the GPU. Actually, same with the Ryzen as well. So you can run some workloads on the NPU, and you can run other workloads on the GPU in there. And the M5 has 153 gigabytes of bandwidth. And then I think the M5 Pro and Max and Ultra, whatever other chips that they will announce later, will likely be bigger and have more memory. I had a slide about Intel. I seem to have missed it. So Qualcomm is also doing this both for their cell phone processors as well as for their laptop product. So the Snapdragon X Elite, that's their flagship laptop product. And they also have this Hexagon NPU. I don't know if this diagram is to scale in terms of actual die dimensions, but again, you can see it's a significant chunk of the area. So they also have very high memory bandwidth on the latest X2 Elite product, and then 85 TOPS NPU, which they claim is the is the fastest on any laptop class processor, and they also have 8 processors in the GPU. It's not very clear from their documentation whether any of these AI type workloads can be run on the GPU, but certainly their NPU is very capable. I don't know what happened to the Intel slide, but the latest Intel laptop products also have the NPU. I did have a slide. I swear I had a slide, and I don't know what happened. Then there's MediaTek, which again is primarily for cell phones. So their Dimensity 9500 series. So that's their latest, because it's a phone processor. It's 85.3 gigabytes per second. So that's a little bit lower than the laptop class processors. But interestingly, they have a dual NPU architecture. So they have what they call their performance NPU, which is this thing over here, and then they have another one called the super efficient NPU. And I think they can do a lot of the sort of the voice commands and things like that very very efficiently in this small one, while keeping this larger one turned off. But then they can turn this on for any kind of applications that demand AI, right? So if you want to do any kind of effects on the pictures you take in your phone or things like that, then I think then this performance core gets turned on. So these are the ones common in laptops and cell phones. Then there's this company called Hilo, which I think is an Israel-based company, and they are heavily focused towards automotive and other industrial type deployments. They're trying to be certified for sort of much larger temperature ranges, right? So for use in any kind of those type of industrial environments, which have dust and temperature type of requirements. So this is not a module, part of some other bigger chip. This is a standalone chip, and sort of their current products at least are modules that are either connected via PCIe or an M.2 type connector, and they have a neural network core, a separate sort of application processor that's the sort of what coordinates everything else, and then they also have a few other units, right? They have digital signal processing, vision subsystem, and then a few other things, all the interfaces that you would typically require on an industrial type product for interfacing to other sensors and actuators externally. And the neural network core itself, depending on the model, is between 25 to 40 tops. And then there's others, obviously, NVIDIA Jetson, that's very popular for robotics and others, those type of use cases. Tesla has their own set of products. The AI5, I think that's the chip that's going to be in the cars for the self-driving portion of it. And they're also trying to do a data center part to do a lot of their own model training for self-driving, full self-driving. They're building their own data center product as well for their own internal use. Mobileye, this was formerly a part of Intel. I think it spun off again as a separate company, and they're also mostly for the automotive sector, AI chips for that. And then there's a Japanese company called Edge Cortex, which is also targeting sort of these industrial things. So, and there's a few others that you can go find, but you know, there's a lot of I think you can appreciate that there is a fundamental theme across all of this. Everybody understands these applications, and you know, it's just how you put together that matrix engine, right? Matrix multiply engine, along with memory, along with networking. How these different companies have gone about designing their chips, and you know, each of them has have some common elements, but then they have their own kind of trade-offs that each of them made for their market. I think that's all from me. I know Kurt has a few things to talk about as well, but we can do other questions now, or wait for Kurt's presentation, and then we can do it together at the end.
There was also a slide that a report that Brian had. I posted the URL in the chat earlier. I'll post it again.
All right, yeah, Brian had some stuff as well.
Yeah. Okay, there's the URL.
I'd have to say this is pretty amazing what you've outlined here. One thing I would like to ask, though, is the Microsoft Medora quantum processor has a TDA built into it. I was wondering if any of these architectures had that as well, or anything leaning towards it.
Not that I know of. I mean, on the I don't know how much of these will map to quantum computing, at least the way these applications are designed today.
Yeah, I understand the quantum aspect is quite different. I guess where I was going was the TDA aspect, topographical data analysis, components being built in. There were a lot of pieces that you had already built into, or that were built into these architectures at the mobile level and so on, doing different aspects of the processing. And I was trying to see if there were any of them were leaning towards TDA, I guess.
I'm not sure. Yeah, I mean, at least from a graphics perspective, I mean, I forgot to mention one thing, right? I mean, why did GPUs kind of naturally land in this space, right? Because a lot of the graphics processing was historically, you know, a bunch of these floating point calculations. There's obviously a lot of other fixed function hardware for graphics that all these AI specific products stripped out. So if you look at what the AMD Instinct or the Rubin sort of data center GPU is compared to what the consumer graphics is, it's a lot of the same elements, but optimized for compute, right? So you don't have all the pixel processing specific hardware in these pure compute data center type products.
Thank you.
Any other questions?
Unshare. Shankar, I think you have to unshare if I'm going to start sharing.
Ah, okay. I will do that.
Well, thanks, Shank. Thanks, Shankar.
Thank you.
Oh, can you email me the slides tomorrow?
Yes, I will do that.
Okay, thanks. Okay, so great. You can start anytime now.
Alrighty. Let me see. I'll probably do the same way Shankar did it. I won't go into slideshow mode. I'll just do this. Can you see it now?
I'm just seeing a black tree. Oh, there we go.
Yep.
Nice.
Okay. Oops. I'll jump up. So I'm kind of putting this in. This isn't a great fit with Shankar's presentation, but I will highlight some of what he talked about. But I just wanted to memorialize this. I'm really talking about just 2 of the really 5 to 10 aspects of next generation arithmetic that I think might be interesting to this group. Certainly to Linux folk and to Linux processor folk. I think we can talk about. So I'm not going to do a deep dive on any particular aspect of it. However, you can go to posithub.org. I strongly recommend. We had Professor Gustafson spoke at Cooper Union earlier this year, and we have a friend there, Dean Barry Shoup, that arranged for him to speak. And they actually have an undergraduate class on computer architecture there, and the students design a RISC-V, and occasionally they put POSIT processors into it, and then they run over to Skywater in Minneapolis and they fab a chip. It's just remarkable that you can do this now at the undergraduate level. And I do evangelize quite a bit of RISC-V architecture and some of the advantages we've got there, but it seems to me that there's a natural fit between some of these next generation arithmetics to replace the IEEE 754 standard and RISC-V. And to a lesser extent, Shankar, I'd love to talk to you sometime. There's lots of usage cases where, you get the GCC that AMD has optimized, and you link it against a soft POSIT library, and you get equivalent or better performance, depending on your definition, as something that is linked against hard float. And I know while I'm saying that I do a lot of venue shopping. There are codes that we get a 3-way win on, performance, memory usage, energy usage, but those aren't general applications. I'll navigate through a bit and talk about what I consider to be some of the optimum places to be able to use one of these next generation arithmetics. Well, and I, in particular, am setting up a foundation to be able to ensure that the standard remains relatively pure. I don't think Professor Gustafson's at Arizona State University, and he's an emeritus. I think he's mostly retired, but he goes out and he does presentations mostly around this book of his that just came out a year ago, and there's a lot of opportunity to lock down. We do have a standard, but it's only 11 pages. I think we probably also have to standardize some of the implementations of it. The first half of this book, and I can, certainly I can share. I've got like 2 copies of the book. I think Alex has a copy. I can lend one of mine if we have a library, Jerry. I can lend one to the BLU library. The first half of his book is why floating point sucks, and he doesn't get into why the alternatives are good until after we really define what needs to be fixed. And if you teleported down to Earth from Omicron Persei I8 and you said, hey, I've been looking at the computers you guys use here, and you've got 16-bit and 32-bit registers to hold your numbers, but why didn't you guys use digital computers, or God forbid 36-bit computers? And the answer is we did. And 50 years ago, the IEEE sat down with 40 or 50 stakeholders in the numerical notation crowd, which was a lot of computer companies back then. And they said, let's all agree on something so that everybody doesn't have to come out with their own compiler when they ship their servers. And they said, okay, well, we have this phenomenon that it was kind of like, what did they say? A camel is a horse built by a consortium, and it's because there's something for everybody on a camel, but it's not optimum. So, and that's exactly what happened. They mostly Intel and UC Berkeley drove the discussion, but there were a lot of carve outs for people that needed a little bit more, I need a little bit more precision on these kind of operations, or these opcodes are fundamental to our business model. So the IEEE 754 standard, which has only really been revisited a couple times, 2008, they looked at it and they said, okay, well, we'll make some minor, not all that really backward looking modifications to this. So it needed a rehaul, a complete rehaul, many years ago, and it certainly does now, thanks to the way that the industry has run with the floating point format. Now, so let me tab down here to. So if you pop open Python on your laptop of choice, you almost certainly are using hard float. It's been a long time since a processor shipped that didn't have a math accelerator on die. When x86 and 8087 as a math coprocessor came out, they were separate, but they found out pretty soon after everyone agreed on the standard that they would just integrate this particular resource and a lot of other ones. Consolidation into the SOC started a long time ago. It's manic now, but North Bridge, South Bridge, everything ended up in the system on chip. So you might as well use hard float. It's there. It's faster than using a software math library, but you get data representations that are off brand, and quite often, depending on the application you're running, you may not know that that's going on. But it fundamentally comes down to the way that we're storing these numbers in memory. So even with 32-bit, so 32-bit nominally, you if you weren't really doing a whole lot of modifications to your code, you just grab float as your data cast, and you'll say, okay, well, this should be fine. And hey, it's 32-bit. It's probably going to be pretty fast. Well, there's plenty of operations that 32-bit is going to give you an error, and here again, there's plenty of usage cases where throughput trumps fidelity. And I don't often use the word trump and fidelity in the same sentence, but there's NVIDIA certainly has kind of cornered the market on looking at things that need to be knocked down from 64-bit to 32-bit to 16 to 8. If you remember from Shankar's slides that we saw quite recently, there was a lot of these systems that are fixed at FP8. So if you're getting these kind of errors at FP32, imagine, and sometimes you do have to imagine because they're not obvious, what kind of errors you'll be getting at FP8. Now, I was down at Micro Center a couple days ago, and they're selling the DGX Spark, and that uses FP4. So I know that's really fast, but electric bicycles are fast, and I wouldn't run the National Weather Service on my electric bicycle. So I'm not really sure. We're kind of in reductio ad absurdum in some of these applications now, because at the end of the day, especially in market verticals like financial, fintech, and quantitative computing, you probably have a very low tolerance for even minor errors. So the next generation arithmetic, generally speaking, and if you get the Every Bit Counts book, the fundamental aspects that Gustafson tries to fix in the floating point legacy is you can guarantee accuracy and reproducibility. And so certainly you can't do that with IEEE 754, despite the fact that it's a standard, because a lot of manufacturers have implemented the standard their way. And we have even found, there's a usage example in the book about how a code gave different results on an Intel box versus an AMD box. This was a couple of years back, and I don't think he does a real deep dive into the exact error or the source of the error. But like I say, there is plenty of other examples on where he's finding sources of errors in the rest of the IEEE standard. So Google and NVIDIA have said, look, a lot of our usage cases require performance, especially so that we can bandy about the term petaflops, which used to be the exclusive purview of the top 500 high performance LinPack codes, and they for a very long time in the supercomputing and HPC business, they enforced a kind of a native 64-bit double precision standard that was so it was x87 FP64, but they wouldn't allow you to do any sort of iterative tricks to try to get to a 64-bit answer by manipulating 32-bit registers. That isn't really, not a lot of people chasing the HPC LinPack benchmarks anymore. They're looking to speed up an LLM algorithm or something else where a lower precision is tolerable, and quite possibly you don't lose accuracy with a lower precision. That is something of the sales pitch of posits, is to be able to say, well, we can give you FP64 equivalent with posit 32. So we get the 2x speed up. That's a bit of a generalization. At least on paper, you'll get a 2x speed up by going to a 32-bit representation, and then not have to lose the accuracy or the reproducibility. There's a bunch of things that the POSIT standard has adopted, and like I say, if you watch that Cooper Union video, that'll all be in the early slides. They don't use the two kinds of not a number that floating point supports. They have just the trap, not a real. So there's plenty of things that floating point calls not a number that are actually numbers. They're just not real numbers. For the 400 HPC codes that we at the POSIT Foundation will be looking at when we get off the ground, we're going to try to find, certainly summer students, to kind of look at the data we're working with. Go to Hugging Face, download that massive data set that you need, and then characterize it. Look at the histogram. Is it a typical bell curve centered around -2? Fine. We've got something, numerical notation for that works way better than floating point. Floating point will give you the same, 16 bits of accuracy at 10 to the -26 and 10 to the +26. We don't need that. Most of what we humans work with are numbers that are around 0. And so POSITS gives you much higher accuracy around the center of the bell curve. Way out on the fringes, like I say, a standard bell curve, we don't, there's not a whole lot of reason to represent those numbers as accurately as floating point does, if the trade-off is less accuracy for the numbers we do use. And that's a pretty strong pitch. We handle the errors the same way floating point handles them. It's just that we don't get anywhere near the number of conditions for that floating point does. And here again, I know I'm speaking in generalities, but there's some really, if you watch that video that's on YouTube by the students some undergraduate students in the summer worked for a group called the Summer of Math Experience internship. and they put together a pretty decent comparison of posits versus floating point. Now this was all from information that they culled from public resources, in particular stuff that's on posithub.org. Gustafson's 2 books. This was his first book. He described Unum Type 1 and Unum Type 2 in this book. Doesn't have anywhere near the application that Unum Type 3 posits does. He talked a lot about interval arithmetic and stuff in this book. It has application, and I guess if you had to solve a particular problem and you wanted to build a Unum supercomputer, it would be no more or less work. At least since not a whole lot of companies are shipping POSIT processors right now. There is one Indian company that you can buy a processor that has 8 RISC-V cores and an equal number of POSIT cores, and be able to run hard POSIT on that. Here again, you got to use the correct flags, or better yet, open up your code and make the right changes to the data casting, and then compile it through the compiler that they give you. But one day, and this is certainly something that the RISC-V Foundation is considering, there'll be a company that says, look, we'll just use the floating point registers, and we'll somehow adapt our POSIT notation into it. Now, here again, you'd have to make some pretty substantial changes to your code if you wanted to handle some of your data as posits and some of it as floating point. You could. We don't quite have a solution yet where you can say, okay, I'm going to drop this code that has 3 or 4 different kinds of numerical notation represented in it. Maybe you had John's first book and you're using unums and valids, and all of these numerical notations were designed to speed up an inner loop, or to use half the RAM that it was using prior to the conversion from floating point. I think our pitch is there's plenty of opportunity just within our arm's length right now to be able to make speed ups without buying new hardware, or using the cores that Shankar described that could possibly be a source of errors. If you're using an NPU that only gives you FP8, you really may not know that your data's not correct. They always I forget what the check machine is for a lot of these top 500 HPL runs. I think they look at your run and they go, okay, well, let me check your results against the bog standard, which is probably a big bull machine in France somewhere. I don't know how they check the 64-bit stuff, but a lot of this 8-bit and 4-bit stuff, no one's comparing. No one's saying, okay, well, I've run this on an equivalent FP8 machine and I've got the same result. No one's even checking those, because to be quite frank, we know they're wrong if they're using IEEE 754. Anyway, I just wanted to throw that out there. I'll be over the summer. I get through the RISC-V Foundation. I get interns, and we can decide what chunk of either RISC-V acceleration or maybe some other acceleration we want them to work on. And we're substantially looking at just doing this in software first and utilizing whatever we can get out of the RISC-V processor. But eventually we'll be able to submit an extension. Maybe we'll call it the POSIT extension for the RISC-V API. Yeah, that'd be great if we could do that. Not necessary, this year. Like I say, we're going to pick some codes that we can accelerate substantially just by using a soft POSIT library, and we're not going to worry too much about how we would do if we had hard POSITs. We're just going to say, hey, we've got a code here that doesn't have any real competition right now, because this is a code that runs terrible on the existing architectures, and it runs pretty good when we use POSITs instead of floating point. Yeah, so that's my spiel.
Hey, thanks, Kurt.
Thanks, Kurt.
Oh, Kurt, can we post your slides on the Blue server?
Yeah, sure.
Okay. So you can fill in.
Okay. Yeah, I haven't done that in a while. I just sent them to you, or how do I do that?
Yeah, just send them to me and I'll post them.
Okay, sounds good.
Mm-hmm.
So, Kurt, do these soft POSIT libraries use CPUs, or are they GPU-based, acceleration?
So the one that there's a couple of options. The one that's on
I guess it's
POSIT
just it's like, is it vector or is it not vector?
Oh, okay. So certainly not the latest RISC-V vector, not yet. But these are mostly the Stillwater Supercomputing Universal Libraries, and that's getting a lot of updates, and it'll have more this summer. And I may ask you to consult to me a bit on that, because I don't even think that they had taken a look at it back before the vector standard was approved. So we'll have to lean into that this summer.
But it's not like back-ended with CUDA or ROCm or something like that, or Cyclophone.
Yeah, ROCm would be great. That would.
It's not. It's not now. I'm looking at the GitHub page right now, but I'm not familiar with it.
Yeah, are you looking at the Stillwater Supercomputing page? That's
Yes.
where. Yeah, so we're gonna fork that, and I think I don't know if you noticed, like the lead programmer there is somebody called Claude.
Okay, I'll take a look at it, because they got a matrix library here, so I assume it's fine. CUDA.
I can drop that Stillwater Supercomputing GitHub link into the chat. That's a really well supported. There's a lot of not a lot of people working on it, but there's updates on that every day. Let's see if I can find that.
Yeah, there you go. I shared it.
Okay.
Kurt, do you want to show Brian's report? I think he said in the email that he just wanted to provide it, but he didn't want to show it himself.
Do I have that? Let me
I put the link in the chat a while ago.
Okay.
A little bit. I got to put it again.
Yeah, I think I'm not sharing now. Do you want me to reshare it? I could do that.
Oh yeah, reshare your web browser.
Okay.
And okay, just put the link in the chat again.
Alrighty, hold on. Let's see. Oh, there it is. All right. Fact4JI. All right. I might have to, well, I can scroll down at least this far. Might have to. Oh, yeah. That's a pretty good scrape. I did notice that there was a, I was going to tell Shankar about this. He didn't talk too much about third-party PCI cards, but there is a Thiel Foundation startup in Cambridge. So Peter Thiel gets these kids to quit college, and then he funds their startup. This is he's got a pretty long tradition of doing this, at least 10 years, maybe more. but there were 3 or
I think
4
he has a
Harvard.
few dollars in his pocket, right, for that.
Yeah. So there's a couple of kids who quit Harvard and started. I think it's etch.ai. Let me see if etch.ai is the right URL. So they've got an AI accelerator that's a complete ground up. Let's see, etch AI PCI card. Let me see if this is.
I mean, TenStorrent has a PCI card version as well. I think a few other companies do.
Oh, etched. Okay. Well, it's a big company now.
20 million.
Hold on. It looks like here. Let me share this tab instead. Okay. All right. Well, there's no info on this slide, but they had a notional design of their PCI card for a while. It's called etched. Well, they got jobs.
Yeah, but if you look at the picture closely, I think some of these guys have 6 fingers.
So it could be AI or it could be radiation. Or thalidomide.
I know a guy that had 6 toes.
It's Cambridge. It could be both.
He was a doctor at Mass General.
Yeah, wasn't that one of the side effects of that thalidomide poisoning went on back in the 70s? Or was that the 60s?
No, it was the opposite problem. Pregnant women would have kids that had somehow stunted their arms, and yeah, that was more of a problem. I understand in the UK and Europe. I don't think the US had. I don't think we adopted thalidomide as. Well, what was it? Was it a relaxant or something? I forget what the off-shelf application was, but yeah, that a lot of the thalidomide problems were in the UK.
I mean, it's like the epidural of today, right? At least that's the way I understand it.
Anti-nausea.
Yeah, anti-nausea.
I must remember hearing about it when I was like 12 years old back in the 70s, and I never really understood the details.
Oh yeah, yep.
So, Shankar, do you know how AMD is finding support from the different Linux distributions like Ubuntu and Red Hat for kernel updates for these AI cards from NVIDIA and AMD? Are you guys having a hard time working with the distros at AMD?
So, I mean, the one thing nice about all the AMD stack is it's all open source, and so all the changes do get upstreamed. And at least from what I understand, most of the qualification happens on Ubuntu and Red Hat Enterprise. I think those are the 2 most common ones. And the ROCm distribution, everything gets distributed via. I mean, I think the AMD, if you include the AMD, distros, the package servers, then you get more up-to-date ones, but a lot of them also get upstreamed into the distros repos.
Do you mean their direct repos or something like ePel? I only ask because of where we can get our stuff from.
I mean, the best place is to just go to amd.com and get it from there. Those are the most latest and tested ones. And then there's also, if you don't want to, for example, PyTorch, there's also like Docker images that you can use where everything comes integrated. I mean, you still have to install the GPU drivers and the ROCm stuff separately, but if you don't want to go through all the hassles of setting up PyTorch, for example, you can just download the Docker container.
Gotcha.
I can send you a link. I mean, I've been playing around with things on my personal desktop with a Radeon GPU, and so far I haven't had many issues. Initially there was, but I think with every successive, as long as you stick with what is recommended, I think it's a relatively smooth experience. So
I know
right
Ubuntu
now,
has PPA, package management. If you add the PPA to it's just like Apple, but it's a little bit better maintained. If you add PPA to Ubuntu, you can get the latest drivers and kernels. Just support ROCm from AMD.
That's true. Yeah. I don't know if there's a PPA for that. But you can download .debs directly from amd.com, the developer site.
Yeah, there is a good PPA. There's a good one. It's like usually 1 week or 2 weeks behind the official AMD website releases.
I see. Okay. Yeah, but I mean, it's a great time to to be in this business, right? The number of people truly interested in building large-scale computers, like Cray and the type, right? They're very limited, and now everybody and their brother has to do it. It's great. There's memory shortage. I'm waiting for fiber optic shortage next.
Yeah, Dell won't even quote out computers to us right now, straight saying they're on memory hold. So we can't even get a quote anymore.
Yep. I mean, I know even on from our discussions, like a lot of these guys are now saying we'll only populate a single DIMM. Even though you have dual channel memory, they will only populate one DIMM, for cost reasons. So yeah, you're going to leave performance on the table because you're only using half your memory bandwidth. So that's not good, but that's what's going on. So if you didn't buy DRAM before September or October last year, you're in for a rude shock. Same with SSDs, right? All the flash prices have skyrocketed as well. So Kurt, I was thinking about Brian, we did the budget builds, right, a few years ago, and now you need a drastic redefinition of what a budget build is.
Oh yeah,
just memory and storage will be like north of $400 for a reasonable system.
Yep. Yeah, I had heard that Western Digital basically sold its entire run of SSD to somebody, X.AI or somebody.
Yes. Yep.
Yeah, we went up at least a third in our quotes over the last couple months, and then finally they're like, we're not even going to quote at this point, and that's all due to memory and then hard drives.
Yep. So I mean, if you want to if you want to get a laptop with like 16 gigs of RAM and even like a 512 gig SSD, prices have doubled in the past 6 months.
I know Alibaba just raised their cloud prices 30%, 30 to 35%. I haven't seen a raise from Amazon yet, but that would definitely make things interesting if Amazon suddenly tripled their prices for AWS services, which I can't imagine how they would not, given what I've seen. Yeah, is SSDs are 2 to 3 times as expensive as a year ago, and RAM is 5 to 7 times as expensive, probably.
Well, it'll cause a lot of interesting innovations to come about now that things aren't affordable. People get creative.
We were joking at work that maybe finally software folks will become more parsimonious with memory.
I don't see that happening.
It's a hardware person joke.
So if you can talk about it, Senator, is AMD doing anything with integrated optical communication between their chips? Have you started experimenting with that? I know it was one of the things announced by NVIDIA at their recent conference last week.
I don't know how much I can say publicly. Answer is yes, but I'll leave it at that.
Understood. Thank you for the info anyway. Yeah, I mainly do, I've been doing everything I do with NVIDIA cards, but I've been thinking about moving more with AMD just because of availability and cost. And it's mostly hobbyist stuff at this point, but I'm trying to decide whether to learn Rockham or Sickle. And I think that maybe Rockham is a better choice. Because Sickle it's not moving as fast as CUDA and Rockham. I think I'm going to drop off, but I really appreciate the talk, Sangdar. It was very interesting and informative.
Yeah, thank you.
Yeah, Shankar's got his ear to the industry's heartbeat, I think.
I actually lost my connection here on both of my machines. I think we're still recording on Driftwood, though. But Vince's not letting me connect to it for some reason.
All right, I'll see you next month, John. I'll email you the slides.
Okay, thanks. See you then.
Yeah, see you all next month. I'm going to drop off too.
Okay, thank you, everyone.